Hello everyone! In this video we will continue to examine topic 4.4 wave behavior, and in particular we will introduce the phenomenon of refraction. Refraction, as opposed to reflection, and unfortunately they sound similar, is the bending of a wave at an interface between media due to a change in the speed of the wave. This is traditionally thought of with respect to light, but refraction is a phenomenon that applies to any wave. And in fact, we will figure out why. So if you understand why refraction occurs, you'll understand why this would be true for any particular wave. Refraction is traditionally diagrammed like so, with a ray diagram. And in the ray diagram, you show an incoming wave or incident wave with a ray forming a particular angle of incidence, theta I, to the normal, as it travels through medium 1, through a particular medium. Then, when that ray enters a second medium, in this case, a medium in which the wave speed is slower than in medium 1, that ray is bent, and it is bent to an angle theta r, shown here. In this case, it is bent inwards, towards the normal. So in this case, it is bent that way rather than this way. To understand why this occurs due to the speed of a wave, we're going to consider a diagram. But before I do that, just a few words about seeing refraction in everyday life. We actually see this quite often. Anyone who has looked through glass from an angle or looked through water in any way is familiar with this. This is the phenomenon where straws seem to bend at the surface of a glass, or fish are not quite where they seem when they're in the water. My favorite example is sort of refraction is seen from the corner of a fish tank, something like this. So if in your fish tank you have a fish or a coffee mug and you look at the corner, you'll actually see two fish and two coffee mugs because the light is being bent by that interface between the water and the glass and the air. And so you actually see two versions of the same thing. This is an extreme, but pretty commonplace example of the refraction of light. So, to understand this phenomena, we will actually, return to this particular simulation. So this simulation is showing a wave packet as it runs into the boundary between a fast-moving medium and a slow-moving medium. Now, the first thing to notice is that the waves in the fast-moving medium, sorry about that. Let me just clear the waves here. So the first thing to notice is that as the waves travel through the fast-moving medium and hit the boundary, some significant portion of that wave reflects offwards, off of it, and returns to the original medium. And you can see that for that reflection, the angle of incidence is equal to the angle of reflection. So theta I equals theta r. However, for the portion of the wave that is transmitted into the slower moving medium, you can see that that wave continues onwards, but in a slightly different direction from its original direction. It's bent towards the normal. And this simulation makes it clear why that is. To see that, consider the portion of the wavefront that first reaches that slower medium. That part of the wavefront that first reaches the slower medium is going to slow down first. But the rest of it, of that wavefront, is still in the first medium, and so is still moving fast. As a result, it's as if that first part of the wavefront is stuck in molasses, is sort of dragged backwards, and the rest of the wavefront catches up a little bit. That is fundamentally why that wave turns. Sort of as if you were walking somewhere and somebody grabbed your hand pretty significantly, you would turn into them a little bit. This is the same phenomenon here. Notice also that the wavefront decreases as that wave slows down in the second medium. Sorry, the wavelength decreases as that wavefront slows down in the second medium. This general phenomenon of refraction can be seen in the wavefront diagram as well. So in truth, this is due to its wave properties and is perhaps better represented by the wavefront diagram rather than the ray diagram, but the ray diagram is much more succinct and is the usual way of representing refraction. Notice that with the wavefront diagram, every wavefront is drawn perpendicularly to the ray representing that wave. And you can see that the dark blue section of the wavefront, which reaches the slower medium first, is bent compared to the light blue section of the wavefront, and in particular bent towards the normal, as that wave is going from fast to slow. Consider what would happen if the wave was going from slow to fast. Well, you would simply reverse the arrows on these rays, and the wave would bend outwards and away from the normal. So this diagram is more or less simply inverted. You can imagine a wave coming in from the slower medium bent outwards, away from the normal, as it goes into the faster medium. This relationship between theta I and theta r can be made mathematical using a principle called Huygens principle, which we'll come back to a little bit later. But empirically, it is the case that the speed of the wave in both media are related to those angles. And in particular, v1 over v2 is equal to sine of theta 1 over sine of theta 2. Here we're using 1 and 2 to refer to the two media, partially because it doesn't matter whether one is fast or one is slow, or which order the wave is going into, whether it's going sort of downwards or upwards in the diagram, but also because theta r already means the angle of reflection. And so sometimes for clarity's sake, with refraction in particular, we will use theta 1 and theta 2. We will discuss the consequences of this mathematical relationship in the next video.